Welcome to the deep dive. Today we are undertaking a monumental task. We're tracing a 3-decade scientific quest that started way back in the late 19th century.
And it's a quest that really did reshape physics.
It did. And our source material for this is the incredible 1913 Nobel Lecture by Heike Kamerlingh Onnes. It chronicles his systematic, and I have to say, painful-sounding technical march toward absolute zero.
It's a spectacular paper. It's not just a discovery announcement, it's a technical memoir of how they built the world's coldest laboratory.
Right.
I mean, before Onnes, scientists were struggling just to liquefy common gases. His goal was radically different. He was chasing extreme cold to enable fundamental physics experiments to essentially suppress all thermal motion.
And he wasn't just guessing, right?
Yeah.
The sources really emphasize he had a theoretical blueprint guiding him.
Precisely. His entire enterprise was guided by van der Waals theories, specifically the law of corresponding states.
Okay, what does that mean in simple terms?
It basically suggested that if you looked at all gases relative to their own unique critical points, their temperature and pressure points, they'd all behave in a similar way.
I see.
So that gave him the intellectual confidence that even the most stubborn gases like hydrogen and, eventually helium could be turned into liquids. It gave them a target and a method.
And that theoretical framework demanded just flawless execution. The source material keeps hitting on this idea of continuity.
Yes.
The mission of his Leyden method wasn't just to produce a batch of cold liquid, but to create these continuous permanent baths for experiments. Why was that steady state so critical?
Because physics experiments, they aren't instantaneous. You need a stable environment to measure something like electrical resistance or spectral absorption over time.
Of course.
So Leyden developed what they called the Leyden process, which was a closed circulation system. If a gas evaporated, it was immediately recaptured, sucked up, and reliquefied to keep that bath constant.
So it was the invention of refrigerated permanence.
That's a great way to put it, yeah.
When you look at the schematics in the source, this cascade system sounds less like a lab setup and more like a specialized industrial plant running 24/7.
That's a perfect description. It was a massive piece of infrastructure. It was a cascade because they used a sequence of cooling cycles, each liquid gas serving as the condensing agent for the next one.
So one thing cools the next, which cools the
Well,
next.
exactly. They started with methyl chloride, cooled by water. That cooled ethylene. The ethylene then cooled oxygen, which, when it expanded, could produce liquid air.
And what did this whole complex setup actually achieve?
It supplied a huge amount of continuous cooling. We're talking about 14 liters of liquid air an hour. And it could maintain constant temperatures down to minus 217 degrees Celsius for as long as they needed.
Wow.
And this stable cold, coupled with Dewar's invention of the silvered vacuum vessel, the de Boer flask, that was the key. Without Dewar's genius, all that manufactured cold would have just, vanished immediately.
And to understand the scale of the precision here, they weren't just cooling things. They were performing fundamental measurements of state.
Right, that was the whole point.
The source material describes the manometer they used, a series of mercury manometers arranged over 45 meters in height. 45 meters? Why on earth would you need a machine that tall?
Because they were measuring incredibly high pressures, up to 60 atmospheres, later even 90. And mercury is extremely dense. To measure small differences in that high pressure accurately, you need that immense height to get a readable difference in the mercury column.
So it wasn't a flex, it was a physical necessity.
A total necessity. And inside their cryostats, the temperature had to be kept constant to within 1/100th of a degree. It's just meticulous engineering.
So once they mastered liquid oxygen, they had to tackle the next big challenge, liquid hydrogen. Dewar had done it first, but the Leyden goal was continuous circulation.
And that was the pivotal technological leap. The cascade system, it wouldn't work easily for hydrogen. They had to adapt the Hampson model, which relies on the Joule-Thomson effect, that sudden high-pressure expansion, to get the cooling.
And doing that continuously with hydrogen sounds grueling.
Oh, it was. It required circulating 40 cubic meters of hydrogen an hour, and that hydrogen had to be impossibly pure. Even a tiny trace of air would freeze solid and instantly block the fine ducts and valves.
But the reward must have been immense.
It was. Liquid hydrogen moved science 5 times closer to absolute zero than liquid air could. It allowed experiments all the way down to hydrogen's freezing point, around minus 253 Celsius. And this infrastructure, it transformed the Leyden lab into the absolute epicenter of low-temperature physics.
Everyone wanted in.
Absolutely. The list of collaborators who came to Leyden is staggering. You have J. Becquerel studying absorption spectra, Bengt Beckmann on the Hall effect, and yes, even Madame Curie came to Leyden.
Wait, Madame Curie was leveraging Onnes' lab? That really grounds the importance of this whole thing.
It shows that his lab wasn't just some specialty shop. It was essential scientific infrastructure. And the work gained even more philosophical significance with the emergence of quantum theory.
Right, with Nernst and Planck.
Exactly. With Nernst's heat theorem and Planck's quantum theory, the work became of prime interest. Because by suppressing thermal motion, they were trying to isolate and test the fundamental quantum character of matter itself.
Which brings us to the final, most ambitious hurdle. Helium. Helium was a total mystery, wasn't it? They didn't even know if it would behave like the other gases.
So Onnes went back to the theory. He determined the isotherms for helium to check if it followed that law of corresponding states.
And did it.
It did, and that gave him the confidence to predict its critical temperature was around 5 Kelvin, with a critical pressure between 2 and 3 atmospheres. Those predictions were his target.
But he couldn't just add helium to the cascade system. This required a completely different approach.
It required what he called one great effort. He had to design a liquefier that bypassed the intermediate cooling stages entirely, taking pure helium straight from room temperature, pre-cooling it with liquid hydrogen, and then using the Linde expansion process to push it over the edge.
Describe the lengths they went to for this experiment.
The purification and insulation were just extreme. The liquefaction chamber had triple thermal protection, heated alcohol surrounding a liquid air bath, which surrounded the liquid hydrogen bath.
Like a set of Russian dolls.
Exactly. And the helium gas itself, which they got from monazite, was purified using Dewar's technique of carbon filters cooled in liquid air, stripping out every last molecule of contamination.
And then the historic moment finally arrived.
Yes, July 10th, 1908. Onnes recounts that when the helium finally liquefied, it looked almost unreal. They didn't even notice it flowing in until the liquid filled the vessel and appeared with a knife-sharp surface.
It was that clear.
So colorless, so faint, it didn't look like a liquid at all. They confirmed the boiling point, 4.25 Kelvin. He had won the race to absolute zero.
And having achieved that, they could start doing physics in this entirely new domain. They reached the lowest temperature yet, 1.15 Kelvin, just by evaporating the helium under extreme vacuum.
And immediately they saw strange behavior. They found a density anomaly. The density of liquid helium drops, hits a maximum around 2.2 Kelvin, and then begins dropping again.
That's odd.
It was a very early indication they were dealing with a quantum fluid, where classical rules just don't apply.
But the greatest, most unexpected breakthrough came when Onnes turned his attention back to the electrical properties of metals at these new low temperatures.
Right. There was this long-standing puzzle. When they cooled platinum wire, the resistance didn't drop to zero like some models predicted. It just leveled off. Onnes theorized this was because of tiny impurities.
And that if you had a truly pure metal,
its resistance might vanish entirely.
So he set up the crucial experiment using purified mercury.
Mercury, because it's easier to purify than solid metals. They froze it into these fine U-shaped capillary tubes and plunged it into the liquid helium bath. The result was genuinely shocking.
It didn't just gradually approach zero.
It fell off a cliff. The technical measurements are staggering, but really it's the conceptual image that matters. At 4.2 Kelvin, the resistance, which was already tiny, suddenly dropped to less than a millionth part of its original value.
A millionth.
That abrupt transition signaled a fundamental shift in the material state. It wasn't just better conductivity, it was frictionless electricity. A state Onnes named superconductivity.
And they pushed it even further.
At 1.5 Kelvin, the resistance was measured at less than 1,000 millionth of its normal resistance, essentially zero. They had found a macroscopic quantum phenomenon, and they quickly found others, like tin at 3.8 Kelvin and lead around 6 Kelvin.
The implications must have seemed immediate and just intoxicating.
Oh, they were. Superconductors made electrical experiments without resistance possible. Onnes realized they could create these self-contained coils that once you charge them, the current would just flow indefinitely. He called them persistent currents.
So the immediate practical promise was huge. The ability to generate unbelievably strong magnetic fields without iron, because there's no Joule heating to melt the wires.
Exactly. They found fine wire spirals could carry these huge current densities. One example was 56 amperes per square millimeter.
But this is where the story gets complicated, isn't it?
Yes. The euphoria lasted only a few weeks because they immediately ran into critical thresholds. Onnes discovered that superconductivity only held below a certain current density.
You push too much current through it
The
and...
normal resistance abruptly reappears, and that often caused rapid heating that burned out the wire.
And then, in a proof added to the lecture, they found a second devastating threshold.
Magnetic fields.
Yeah.
For lead at boiling helium temperatures, applying a field above just 600 Gauss instantly cause large catastrophic resistance to reappear.
So the very magnetic field you want to create is what destroys the state that creates it.
It was the ultimate gut punch to the dream of creating powerful, resistance-free electromagnets.
So Onnes left the physics community with this profound foundational question. Is this critical current and magnetic field effect caused by bad spots, impurities you could engineer out?
Or is it a fundamental property of the metal itself, a core characteristic of this new quantum state? If it was the latter, it meant Ohm's law was effectively invalid under these conditions.
He was asking if they'd simply run into a wall of fundamental quantum mechanics.
That was the question.
What a legacy. Onnes's methodical, theoretically guided work, spanning 3 decades, not only met his original goal of liquefying these unmastered gases, but got us 5 to 10 times closer to absolute zero than hydrogen ever could.
He was a titan of scientific methodology, and in doing so, he delivered the first undeniable evidence of frictionless electricity.
And yet, in the very act of discovery, he defined the challenge that still drives material science today. We're still trying to engineer our way past those critical thresholds. If you look at modern challenges, building high-field magnets for fusion reactors or quantum computers, that puzzle from 1913 is still unsolved.
That's right.
Are these limitations just engineering hurdles waiting for a pure material? Or are they an immutable feature of the strange quantum world we finally accessed, just below 5 degrees Kelvin?